Right, so this is just going to be a little bit of kind of housekeeping when talking about combining functions. Um, what we're going to do is just talk about what happens to the domain when we combine some functions together. Now, 9 times out of 10, when you're asked to do this, you'll be actually given explicit functions like f of x is 2 to the x, and g of x is 3 minus x, and then mash them together somehow. And then what you could do is look at the domain by mashing them together and then seeing what the domain of the new function is. But this is an example of a question where maybe it's a little bit more abstract than that. I'm not actually giving you the functions. I'm just giving you the domains of the 2 original functions without actually telling you what they are. So we can't actually mash them together and get a new formula because I never gave you formulas to begin with. But fortunately, the rule's pretty simple for combining functions, and there's just one little thing that we do need to pay attention. Basically, yeah, what I wrote up here, when we do combine functions, we can't perform any of these operations at the x values that don't exist. So when I'm giving you the domain for f and g, I'm telling you basically both where the function exists and where it doesn't exist. So this here, for f of x, says that x cannot be 4. So this says that f exists for all x not 4. And f does not exist, I'll use that DNE, when x is 4. That's what it's saying. It gives you all the information that we need. And then g is telling us that g exists when x is greater than or equal to 0. G does not exist when x is less than 0. So there's 2 ways that we could actually think about finding the new domain. Essentially, you just kind of compile everywhere where this function doesn't exist. So it's actually the union of all the places that it doesn't exist to find the new total region where it doesn't exist. So you could write so any combo doesn't exist at the union of all DNE sets. Here our 2 sets are the x equals 4 and the x is less than or equal to 0. If we were to actually draw that out, we'll see that there's no actual overlap of these 2 sets. So if I were to write this on a number line, I'd have my less than 0, and then to the left like that, and then a point at 4. So I can't really combine that into one nice clean interval. So this is what I could say is the region where it completely doesn't exist. What I would have to do to finish answering this question, though, is to then actually find where does it exist. Basically, the answer to that is everywhere else. Again, there's 2 ways of figuring that out. One thing that we could do is just sort of fill in this region and just color in what the opposite of this is. So I don't want anything left as 0, but I do want 0 because it's not included in that set. And then I need everything all the way to 4, but I need to skip 4 and then go on like this. So what I could do is write that as I'll need 2 intervals because they're 2 separated regions. And yeah, that's actually our answer here. So what we'll have is the interval 0 to 4. And then I need the region after that. So that'd be 4 onwards to infinity. Yeah, so that's going to answer our question almost entirely. Maybe I'm not quite done yet, so I'm going to get rid of that little final bit there. So this is actually the domain for f plus g f minus g and f times g. So we're not quite there for f divided by g. And I touched on this in the lesson for combining those explicit functions. For f over g, there's a possibility that we divide by 0, so we would also have to exclude any points where g is 0. And again, that's the output, not x itself. So we don't have that information, and unfortunately, with what I've provided you for this question, you wouldn't be able to figure that out. So I'm just going to write a little note. We would also have to exclude any x with g of x equals 0. So yeah, we just simply don't have enough information to do that right now. Another way that you might want to look at this, getting a little bit into like set theory and logic here. So instead of just like piling up all the places where it doesn't exist and then throwing all of that out, another way that we could have actually looked at this is we could actually take the intersection of all the domains. So instead of throwing out the union of the rejects, we could also think of this logically as the only way that the domain exists is if the domain exists for both f and g, which means that it has to be in the set of existing for both of them. So it's in the intersection of those sets. So that's another way that we could think of this. So if I do x is not 4, I'm going to write my number line again, kind of lazily here. So x is not 4 is going to be everything up to 4. And x is greater than or equal to 0. So I'm going to do a closed dot at 0 and then my line like that. And then if I want to talk about the intersection of those two regions, what I can see is it's going to come here. Right to the left of that, I only have one of the regions, so it's no good. That is going to skip over the 4. So I have everything up to 4. And then again, I have the 2 lines everywhere after 4. And then you can see we get the exact same set as we had doing kind of the roundabout way. We get the same conclusion. So it's going to be just sort of whatever you're more comfortable with. But both of those should give you the same answer. But the same issue does occur in both, in that in the division case, we have to be careful because we might lose some extra values. But if I gave you f and g, you would see that immediately, because you'd see like we're dividing by x plus 1, so I need to reject -1 as well, or something weird like that. So yeah, these types of questions aren't really practical for what you'll likely end up doing in higher level math. It's just something to think about.